Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we will be looking at using the RungeKutta technique for solving higher order initial value problems. So as a reminder, we can set up an ordinary differential equation so that it is written as a function of x, y, and as many derivatives as we have equal to 0. And the highest derivative in that expression will be the order of that differential equation. Our goal then, of course, is to find the, in this case, y of x that would satisfy this equation. And we have categorized these ordinary differential equations as either initial value problems or boundary value problems. And for first order, it really didn't make any difference. They were always an initial value problem. For higher order, it depends on whether all of the boundary conditions are at the same value of x or are they at different values of x. If they are at the same value of x, whether it's x equal to 0 or some other point, then it would be categorized as an initial value problem. And we will be looking at a technique for initial value problems in this lesson. We also have already looked at the RungeKutta method, but we're doing it for first order initial value problems before. And with h as the step size, we end up with this expression here where these various k's are functions of x and y that are roughly a half step or a full step away from my original point. What we want to do now is extend this to higher order initial value problems. Basically, what you're going to do is make a substitution for the n minus first derivative of y. And you would continue doing this if you had multiple derivatives, but make substitutions for the derivatives and then rearrange the function so that you have the second derivative is now a derivative of that function z. And a second differential equation is, in this case, dy dx equals z. So now we have a system of two first-order differential equations. Now, we didn't talk yet about solving a system of first-order initial value problems. They can be done by the RungeKutta method using a similar technique to what we were doing, but we're going to be doing our steps, plus half a step, and so forth, for both the y and the z variable. And we will apply it to each of those. And this is the way it's written out in our booklet. An alternate form that I think is perhaps a little bit easier uses this form. Now, these k's are not quite the same as we had before because they are multiplied by the step size. Before I had multiplied the step size outside of this. But it's the same expression if you look at all of the terms. And we have a term for y and for z. And so what we're going to do is we're going to step from, if our step size was 0.1 and we started at 0, we'd go 0 to 0.1 and we would calculate y and z, so y and y prime at that first little one step size away. And then we would do this for the two step sizes away from our starting point, and 3, and so forth. So I have this for my y and I have this for my z, where z was my first derivative. And I end up with these two expressions, which are really identical, just that one is for the y function and one is for the z function. Now to solve these, because of the interdependence, you've got to kind of take a closer look at the ordering. And so you would need to do the k0 and the l0. And then those are used in k1 and l1. So do these in little groupings. Once you have all of those done, then you'll calculate y and z for that next step. And then you go back and begin again for the next little step. We're going to apply this to this example here, a simple constant coefficient second order ordinary differential equation. The second derivative of y plus 6 times the first derivative plus 9y is equal to 2. And our initial conditions in this case are y of 0 and y prime of 0 are both equal to 0. So what we want to do is say y prime is equal to z. Now this z will be a function of x, y, and z, so that's going to be my first equation. And then my second equation says that y prime prime, which is z prime, is 2 minus 9y minus 6z. So the derivative of z is 2 minus 9y minus 6z. And that's going to be our second function, g. Now let's look at Excel. I have set this up already so that we don't have to watch me type. I've set up my starting value of 0. My initial conditions were 0. I'm using a delta t of 0.1. We'll just go up to a t of 1. And I have my function. So let me pull up my code, bring it over here. Now, most of this code really was the same as what we had before. All right, I'm reading the numbers, but now in addition to reading YA, I'm reading Y prime from the original screen. So I need an extra initial condition to read in. The rest of all of this, initiating everything, is the same as what I had before. Now I start my loop. And so for each of the steps that I'm going to take, I'm going to calculate K1, L1, K2, L2, K3, L3, K4, L4. And then use those to calculate Y prime and Y. Now Y prime is what we've called Z in the notes, but I'm calling it Y prime and I'm just treating it like a variable. And so that allowed me to visually keep track of where the first derivative was. So I'm going to estimate y prime and y, and I'm going to estimate my next x. Now I have two functions. Because we had already had a function that said deriv equals, I just called them deriv 1 equals and deriv 2 equals. Deriv 2 equals is the g of x, y, and z, or y prime. This is the one that you'll want to change, okay? This one right here. The deriv 1 equals is just going to be that the derivative of y with respect to x is equal to y prime, or my z, the way we were handwriting it. So if you are doing second order differential equations, you don't need to change this one. This would be the only one that you change, and this is your function. The derivative, or the second derivative of y, or the derivative of z is equal to this. Okay? Now, if I do this and I run this, and I can bring this up. If I run this, I guess I didn't put a heading over there. This is the y prime so that I could track and make sure it was calculating those properly. But we have an estimate here, and it does indeed match what you would expect to get. This is a well-known problem. So we have that. Now this actually can be adapted also for doing a system of differential equations. And I would basically read those in. I'd have to make some minor modifications up above in what I was reading in. But this could be for function 1, this could be for function 2, in which case I would want to edit this. But for now, we're just worried about being able to do a second derivative or second order differential equation. So this concludes this lesson. Thank you very much for your time.